Good morning, everyone. Happy Friday. You know, for most people, if they need to learn a new skill or a new task, something like how to fix the sink or how to learn a new language, and you present them with a choice of either doing it with text-based materials or a video, most of them will choose video. And it's not surprising, given that with video you can visualize more complex information. There's motion as opposed to everything being static, whether it's an image or text. And so as a result, video is being used more and more for training, for learning, for corporate communications. And yet, most businesses don't use video as much as they could or should. And really, the single biggest reason why that's the case is that traditionally, long-form video has been impossible to search. The content within the video has been impossible to search. So that's what we're going to be talking about today. Searching inside video and doing it at massive scale without breaking the bank by using spot instances. My name is Ari Bixhorn, and joining me today is Tim Sullivan, our VP of Engineering. We work for a company called Panopto, and we build a video platform that, among other things, does video search. All right, so specifically, what do we cover over the next 40 to 45 minutes? I'm going to start off with a quick overview of video search. What does it mean when we say searching inside a video? What kind of content are we indexing? And why is the way that we do video search now substandard? Tim is then going to dive into our implementation. And when we started doing video search, we had a number of different options for how we could do it. He's going to explain why we chose Spot and some of the other options that we could have used. We'll then discuss our architecture, and we use a combination of Windows and Linux. Tim's going to talk about why we chose Windows for certain aspects and what we're getting out of that, why it's important to our overall architecture. And then last but not least, we're going to share things that we've learned for using Spot to scale up, to scale down, and how to deal with some of the considerations of working with Spot. All right, let's begin by just talking about an overview of video search. We refer to video as a last mile problem for search. And the reason for that is that today, video is really, or multimedia, including video and audio, is really the only data type that is still really, really hard to search. In under a second, you can search over 30 million web pages, 30 trillion web pages. You can search email and documents. You can search what's on your file system. And yet, the non-textual nature of video content has traditionally made it really, really hard to search. Now, when I first started working at Panopto, one of the first questions I asked is, well, hasn't YouTube already figured this out, given that their parent company runs a small boutique search engine? And thank you. The jokes only get worse. But here's the thing. With YouTube, you might not necessarily need to search inside video, because the shorter the video, the less valuable inside video search becomes. So right now, the average YouTube video is about 4 minutes long. So if you find a video and you need to find something within that video, and the video is only 4 minutes long, chances are you're just going to watch the entire video. Worst case scenario, you're out 4 minutes of your life. But it's very, very different in the enterprise. If you think about a lot of the videos that we use in business today, it's things like training videos, compliance training, it's CEO town hall events. And right now in our cloud, we host about 2 million of these videos from both businesses and universities. And most of those videos range somewhere between 15 to 90 minutes long. Now, when someone sends you a 60-minute or a 90-minute video, and they say, here, watch this, chances are you don't need to watch the entire video. You're just looking for some segment within that video that has particular information that's valuable to you right at that moment. So for these videos, we want to start thinking of them less as these big monolithic, opaque objects, and more as a series of segments of information that we can break out and immediately access through the use of search. Now, the way that we've traditionally done video search is through manually entered metadata. So titles, descriptions, and tags. And there's always been a big emphasis on tagging videos. But tags have 3 fundamental flaws when it comes to searching video content. First, tags require the user to think and take action. And as a result, it's not scalable. A few years ago, Microsoft built their own internal, internal YouTube for employees to share information with video. And the biggest problem that they had with this was tagging. People wouldn't tag their own videos. And so as a result, Microsoft ended up bringing on a team of people whose sole job it was to tag all the videos that employees were uploading. So it's not scalable in that sense. The other challenge with tags is that even if you do a great job of tagging your videos, even if you give a video, let's say 10 tags, there's still a very good chance that when someone searches for that video, they won't find it. And I'll explain why in just a second. I'll show you an example of that. And then last but not least, the third problem with tags is that even if you tag the video properly and you're able to find the video, you're finding the very first second of the video. You're finding the start of the video. And that's not what we want. For a 60 or a 90-minute video, we want to find somewhere in that video timeline. And tags don't allow you to do that. All right, so let's look at an example of where tagging, even really good tagging, falls really short for finding a video. Let's use a CEO town hall event as an example. And let's say that the town hall event is 45 minutes in length. The CEO, who we see on screen here, is speaking at about 125 words per minute, which is average speaking pace. And so over the course of that 45 minutes, he's going to say over 5,000 words. Now, ideally, we would tag every single one of those words so that we could search for anything that the CEO said and jump right to that point in the video. But the truth is, we don't need to tag every single word. And the reason is that a lot of words in the talk track don't have any value to search. So I've highlighted those on screen here. Words like the, is, and, your, which. Those words don't have any value to search. So on this slide right here, there are 125 words, 124 words, 62 of them have no value to search. So exactly 50% of the words here have no value to search. We can throw them out. So that means in this 45-minute presentation, over 5,000 words were spoken, 50% of them have no value. That still leaves over 2,800 words that have value to search. So even if you've done a great job of tagging your video, you've given your video 10 tags, let's say, you're only covering a fraction of a percent of the valuable words that were covered in that video. Video search is what we've been focused on at Panopto. So what we do is we build a video-specific content management system that's hosted in the cloud, and organizations use that as an internal YouTube for all of their videos, corporate communication, training, social learning videos, and then in higher education, most of the videos hosted in our cloud are recorded lectures that are made available on demand to students. And what we wanted to do is make every one of those videos that an organization uploaded searchable to the word anywhere within the video. So the way that we did that is we took a 6-point approach. There are 6 types of content that we index within every video that's uploaded. The first is what we were already talking about. We obviously have to index the manually entered metadata, the title, the description, and the tags. We can also index transcription. So when you upload a video, you can request automatic captioning to be done by a human-based service. And this is often required for ADA compliance. So you get captions that play over the video. It's relatively easy to do because what we get is timestamped text back from a captioning provider. But most people don't do transcription because there's a cost associated with it. It's a human-based service, so there's a relatively high cost if you're uploading hundreds or thousands of hours of video in any given month. So that's where things get interesting. One of the things that we do is we run an algorithm that performs speech recognition on the audio track of every video that gets uploaded into the system. And I'll show you a demo of how that works in a second. But basically, we extract the audio content, we run the algorithm, and we timestamp as many words as we can recognize throughout the entire talk track. There's another step here called optical character recognition. And this is particularly important in the enterprise and in higher ed, where videos don't just consist of the talking head, the speaker. They often include on-screen content as well. So it could be a slide deck, it could be an on-screen demo. And what we do with optical character recognition is we look at the on-screen content and we split it up into individual frames throughout the video. Each of those frames is an image that we then run an algorithm on to identify anything that we believe to be text on that image. And when we find text, we add it to the search index and timestamp it. The next to last thing that we do is slide extraction. Now, when you do on-screen content recognition, when you do optical character recognition, it has a very high accuracy rate. So anything that shows up on your screen should, in theory, be indexed. However, we get an added advantage when someone is presenting from PowerPoint or from Keynote. If I'm doing a slide, if I'm presenting a slide as part of my presentation, we can actually tap in to the object model of PowerPoint and extract the text programmatically from every slide, as well as the speaker notes that are associated with every slide, and add that to the search index. So it's like optical character recognition. It's pulling information from the slide, but you get 100% accuracy because we're actually tapping into the PowerPoint object model. And then last but not least, when you're watching a video in our system, as a viewer, you can take notes that are time-stamped and they're personal to you. So anytime you go and watch a video, if you're a student and you want to take notes on a topic while the teacher is speaking, you can take notes directly in the video player. Those notes are time-stamped, they're saved for your playback for future review, and we index those notes as well. So this is the general approach that we take to indexing the content associated with the video and then within the video itself. Let me show you a quick demo of what I'm talking about here, and we're going to look at 3 different things. Let me see here, stand by. There we go. All right, so this is one of our customers' websites, Henry Ford Medical Group, and this is sort of a traditional view of what a corporate YouTube would look like. What I want to do is a search across the entire video library for declining kidney function. What we'll do is return not only the videos where declining kidney function is included, but every moment within that video where the word is either spoken or shown anywhere on screen. So here at 10 minutes and 14 seconds, I'm going to click on that link, and it'll take me right to that point in the video.
Patient population. What about the effect of declining kidney function on the prevalence of sleep apnea and nocturnal?
So you heard the speaker there say declining kidney function. And I used this video because it's an example of how far speech recognition has come in the last few years. The audio quality is good, but it's not great. The speaker is talking relatively quickly, and they're speaking with an accent. And so this ASR technology has come a long way in a really short period of time, and it's made these kind of advances possible. Now let's look at an example of slide extraction, looking at the text within every slide that's being presented and extracting that for indexing. I'm going to search for interoperable, interoperable communication. And you'll see in the search results here, we've identified interoperable communication or variations of it in the talk track. If I scroll down a little bit further, here we see an example where we've identified it on a given slide. And so when I click there and we look at what's on screen, we've extracted interoperable communication from this point in the slide, And you'll notice what's interesting about this is that it recognizes that the words are connected even though there's a line break between them. And then last but not least, let's look at optical character recognition. With our OCR engine, what we do is a couple of different things. One of the things we do is we test how small the font can be on screen and still be recognized. So for this video, what we did is we had a series of phrases on screen, and over time they get smaller and smaller and smaller. And so what I'll search for here, network architecture, and at 1 minute and 40 seconds, what you're looking at here is the word passive network architecture. It's in 8-point font on a 1920 by 1080 screen. And so the optical character recognition is incredibly accurate in terms of being able to recognize text. The last thing that I'll show you here is contrast ratio. We want to make sure that if text appears on screen and the contrast ratio isn't ideal, we can still recognize those words. And so here I'm going to search for HTTP communication. And at 1 minute and 10 seconds, what you can see right here, HTTP communication, and in this case, the contrast ratio is 1.7. And if you look at the Web Content Accessibility Guidelines, it's below that. So the Content Accessibility Guidelines require a contrast ratio of 2.0. We wanted to make sure that we could do even better than that. So that's a really quick overview of what we think of when we're talking about video search and some of the challenges, the way that we approach those within our product. Now let me hand things over to Tim Sullivan, and Tim is going to drill into how we decided to use Spot in the first place, and then some of the best practices that we've learned over the last couple of years.
Thanks, Ari. So way back in 2009, we aspired to be a rapidly growing company. We were quite small at the time, but we thought, let's set ourselves up for success. So we actually started on AWS way back then. And lo and behold, we found ourselves some success. We've been growing exponentially since then. So back in 2009, we'd see 50 hours of content get uploaded to our cloud, and we'd all run around the room and give ourselves, give high fives to each other. We were all really excited about that. And now, in a single month, we're uploading 15 years of content, over 130,000 hours of content in a single month, 400 terabytes added to our content store. And so there's been all kinds of really fun challenges in figuring out how to make our service scale to that degree. The new challenge that we had with inside video search is how do we take this incredibly compute-intensive set of activities to apply to every video and do that in a way that's cost-effective. So the first thing that we considered was using on-demand instances. We had been using on-demand instances for the majority of our cloud, and we were kind of cruising along. We were within our budget, and we modeled it out. What happens if we flip on ASR and OCR? And we were going to blow right through our budget. So this was a total non-starter for us. It was going to be cost prohibitive to offer the new service to all of our customers. And that was really frustrating. So we had this amazing demo. We had this great prototype, and we thought, well, what good is it going to do us if we can't actually give it to people? So then we thought, well, maybe we can just ask people to pay more for it. We could cover our costs and have people pay more if they want to opt in. But Panopto does all of this. And our brand promise is you pay one price and you get everything. It's really simple. So this broke our brand promise, it broke our business model, and so it was a non-starter. Then we considered maybe we can use reserved instances. So reserved instances, for those who aren't familiar, are a mechanism that Amazon gives you to make a commitment up front to run an instance 24 hours a day, 7 days a week, year-round, or some percentage of that. And in exchange, you get to pay a lower rate. So in this case, you can save 30, 40% by doing this. These work really, really well for predictable workloads. We use them for our core databases. We use them for our search index servers, things that we need to run all the time. But they really don't work well if you have a spiky demand curve and if you want to fit to a close SLA. Now, if you don't care about fitting to a close SLA, reserved instances can still be a good option. And we actually tried this for a little while, just to be able to play with putting a little bit more scale on the searching within the video services. So in this case, the horizontal line is the number of RIs. And you can choose to only run a number of instances for which you have prepaid RIs. And what you find is that when you get a spike of demand, you end up with a delayed start to when you can begin processing those workloads. And invariably, there's still some waste, because you need to have a certain amount of spare capacity. And so when you're not actually making use of those instances, you're still paying for them, and there's waste. And in our case, we wanted to have a really quick turnaround time. So it was actually a totally different scenario for us. So in our case, it's common for lots and lots of hours of content to come in during the middle of the day, especially when classes end. If you're a school recording classes, you have classes that end at 9 o'clock, classes end at 10 o'clock, classes end at 11, and you have hundreds and hundreds of hours of content all getting uploaded at once. We want to turn around that content really rapidly. And then in the middle of the night, you've got very little going on. So if you try to apply the reserved instance model to this, you end up often spending more money than you would otherwise, because you're paying to run the reserved instances when you don't need them, and you're paying to run on-demand instances on top of that. So that was a non-starter. We did, for a little while, consider buying our own hardware, but we're all here at AWS reInvent for a reason. The total cost of ownership is a total non-starter. So let's dismiss that right away. Enter spot instances. So spot instances are an opportunity for all of us to buy excess capacity from Amazon at steeply reduced prices. So when EC2 has a whole bunch of instances that aren't otherwise running and aren't being consumed by on-demand instances, they make those available in an auction market. What's the difference between an on-demand instance and a spot instance? There isn't any. The instance itself is identical. They can all run AMIs. You can give them static IP endpoints. All the things you expect from an on-demand instance, you can do with the spot instance. The only difference is in how you pay for them. So on-demand, you're paying one price. It's a fixed price. You know it up front. Spot, you're paying a variable price. You can set your maximum price you're willing to pay, but it's a variable price. So net-net, we modeled out how is our spend going to look with spot, and we found that we could actually hold the line totally flat and open up all these new capabilities of searching inside a video. You might ask, well, you're still doing more work. Why didn't the line trend up? And that's because it turns out we can run a whole bunch of compute that we were otherwise running on demand on spot as well. So when a video gets uploaded, we encode it for distribution on the web. We encode it for distribution to phone. And when somebody uploads a video in a different format, we'll transcode it to our canonical format. And we found that we can run all of those very compute-intensive activities on spot as well. So we're actually doing more and spending less. Let's talk a little bit about the mechanics of this spot auction. So this is kind of a complicated graph. What we're looking at is the market price of the auction for a particular instance type across 4 different availability zones within Virginia. So each colored dot, each color represents a different availability zone. And you can see there's a lot of variation over the course of the day, from day to day, and even variation from availability zone to availability zone. The green line, that's the flat line across there, represents an example bid price. So the basic idea is you bid what you're willing to spend. If you bid more than the current market price, you get instances. If you bid less, then you don't get instances. And in some cases, if you have previously bid a price and gotten an instance, and the market price goes up enough, Amazon can actually revoke that instance back from you and sell it to somebody who's willing to pay more. there are a few considerations if you're thinking about using Spot. The first one is your workload capable of sustaining the volatility that you're going to take on? So there clearly is, when you look at those varying market prices, some volatility. What happens if you want spot capacity and you can't get it? You need to be able to deal with that. In some cases, you can, if your workload is one that can run on a wide variety of different machines instead of just one type, you can potentially use Spot Fleet, which I'll talk in more detail about a little bit later. And then the other thing to look at is for the instance types that you use in the regions in which you run, you can look at the Spot Bid Advisor and see the historical market prices. And that'll tell you if you actually stand to save money or not. Usually you stand to save quite a lot of money. Let's talk a little bit more about the architecture that we use to actually put this into play. So the first thing to consider is the fact that we use Windows to run our service. You might say, why on earth are you using Windows to run a high-scale video service? Almost everybody would naturally say, let's use Linux for that. And the reason we do is that we have a large number of customers that, for a variety of reasons, want to run our service on-prem. Now, we're a small, lean, and agile team. We don't have the capacity to sustain two separate code bases, one for on-prem and one for cloud. So we have just a single code base, a single service architecture. We run it the same way on-prem or in the cloud. And that means it's really important to us that we run Windows in the cloud. And for the most part, it works really well. Well, that's not true of everything. There are a number of cases where we choose to run Linux. One of the reasons that we'll do that is for costs. When you run a Windows instance in AWS, AWS has to presumably pay some licensing fees to Microsoft, and they have to pass that cost along to us. So it's more expensive to run Windows. And there are some software packages that just work better on Linux or only available on Linux. So we're a little bit selective, and in cases where it makes sense for us to run on Linux, we do. But the majority of our system runs on Windows. Now, in the cloud, we try to follow the best practices of running a high-scale, high-uptime service on AWS. And that means spreading our services across availability zones and making sure that we don't have single points of failure. So if a single machine goes down, we've got other machines that can take over for it. If a whole availability zone goes down, we have other availability zones that can pick up the load. And that makes sure that we have service continuity, even in the case of major problems. Now, in this case, if you look at the diagram, there's these green bars that scale out. So we make use of all of the auto-scaling functionality within AWS so that we can turn on and turn off things like video encoding servers, search indexing servers, and our web front-end servers based on load. Let's look at how we actually put that into play with autoscaling groups. So the yellow line here represents, in the abstract, the demand on our services. So over the course of the day, we might get a big spike of demand, a big spike of uploads from our clients, and we need to handle that. So the blue line represents the number of instances actually running within an autoscaling group. And so the blue line will closely follow the yellow line and make sure that we have sufficient capacity to handle all of those jobs. We've found a lot of utility out of using CloudFormation to define and configure our autoscaling groups and really the majority of our cloud. The beauty of CloudFormation is that you can specify all of your config in code. You can check that in code into your source control system, and you can very easily monitor for changes and have good, close review of any changes that you want to make. And with that, you can define everything about how your autoscaling group runs, what instance is running within your autoscaling group, what kind of, which machine image it should run, and what are the rules that determine when to scale up and when to scale down. All of that can be determined and defined in code. Now, what about specifying how to use Spot versus OnDemand in code? Well, this is an example of the launch config for an autoscaling group. So an autoscaling group is just a collection of instances. You can pump metrics in and tell it to scale up or scale down. And the launch config defines what instance and what machine image should be launched and run as part of that autoscaling group. If you look between what's on the left and what's on the right, very little has to change to move from an on-demand instance to a spot instance. Basically, just have to tell the launch config, this is supposed to be spot. And then you have to specify the spot price. So the spot price is that bid price that we talked about. So how do you determine what your bid price should be? We looked at that really complicated graph. And when we were trying to set this up initially, we looked at that and we started modeling out all kinds of numbers and looking at all kinds of historical data. And we were a little bit befuddled. How are we going to bid and have our bids accurately change throughout the day so that we can make sure that we get spot capacity and that we don't overspend? But when we talked to the architects at AWS about this and we looked at things really carefully, we realized since spot is a second price auction, we can use a really, really simple model. If we just bid the on-demand price all the time, it doesn't necessarily mean that we're going to pay the on-demand price. So in this case, you've got the on-demand price is 84 cents. So we're going to bid 84 cents. Anytime the market price is less than 84 cents, we're going to pay the market price. So we're not going to overspend. We're just going to be assured of saving money in all the cases that we're able to. So really simple, right? But there are some challenges to running on spot. One of the things we talked about earlier was what happens, how do you deal with cases where Amazon's going to revoke the instance from you because the market price has gone too high? That's especially challenging when you have very long-running jobs. So in Panopto's case, we're going to be doing things like video encoding, which is a job that might take a half hour or an hour and a half in some cases. Similarly, if we're going to go and run optical character recognition on all the frames of an hour-long video, that's going to take us quite a while. And the longer you have an instance running, the higher the chance that it's going to be revoked from you. You have to have some way of dealing with this. Amazon gives you a little bit of warning. They'll give you 2 minutes of warning if you're going to have an instance revoked. And you've got to be able to handle that. So what do you do? In our case, we came up with this small service that we call Spotter that runs on the instance. So when the market price goes too high, Amazon sends us a message and says, you're going to lose this machine. The Spotter service listens to that message, and it tries to determine, is the job that's already running going to finish before we lose that machine? If so, great. There's nothing to do. But what happens if it isn't going to finish? Well, in that case, you've got some choices to make, and it really depends on your workload. The ideal is to be able to quickly save all of your state so that your job can be resumed and you don't lose any work. Save your state, put it back in the queue, in fact, put it at the top of the queue so it gets picked back up immediately, and then start over. In the worst case, you should at least gracefully cancel the job and stick it up at the top of the queue. So maybe you lose a little bit of work, but at least there's a minimal amount of delay. Now, how do we determine when it's time to turn new machines on? We saw that demand curve, and we saw the instance curve in the autoscaling group slide. How do we determine when to turn things on? It's actually kind of a hard problem. There are all sorts of inputs to consider. One of them is, well, how much work is there to do? How many new jobs are there waiting to be worked on? But there's other considerations too, like how many machines are you currently running? How many of those are currently working on jobs? How long is it going to take them to finish the jobs that they're currently working on? And how long is it going to take you to spin up a new machine if you do need to turn on a new machine to handle the additional jobs? Maybe you also need to take into account how long do you have to turn this job around? What's the expectation of customers to get the results of this job turned around? Now, we started doing a fairly naive approach to this initially, and we found that we had some really interesting oscillations that emerged is we weren't taking into account the time it takes to spin up a new machine. So we'd see a whole slew of new jobs arrive. We would scale up to handle those new jobs. And in the case of some of our Windows servers, we were seeing a 5 to 7 minute delay between when we say, let's turn on a new machine, and when that machine is up and running and actually doing useful work. And in a lot of cases, the machines that we already had running finished their jobs and were sitting there waiting had actually already picked up the jobs that we'd scaled up to handle by the time the new machines came online. So we were wasting money, and then they would just scale back down. So our solution to this problem was give it to the very smart data scientists that we have back at the home office in Seattle and see what they could come up with. They came up with some really great heuristics that we've found have done a really, really nice job at handling all of these inputs and doing a good job making sure that we scale up. Now, how do we tell? We've had a lot of utility out of the CloudWatch dashboards that were released, I think, about a year ago. So we build dashboards for each different job type. If you look at that one at the top in the middle, backend OCR, you can see that we're modeling out how many machines are currently running, and that curve is going up with demand and going back down as demand eases. We're modeling how many of the machines that are running are doing useful work, and we're modeling the queue, so how many jobs are waiting. And so it's really easy for our team to go and look at this retroactively and say, are we doing a good job or are we not doing a good job? You know, is the queue growing too large, indicating we're not scaling up fast enough? Or do we have cases where we've scaled up, but many of the machines aren't actually doing anything useful, in which case we're wasting money? So this has been a really great utility for us. So we talked about how to turn machines on. What about when it's time to turn machines off? So autoscaling groups make it really easy to turn machines off. You just say scale down, and it'll turn a machine off. But it effectively picks at random, or maybe it'll choose the longest running machine. But in our case, that's a really bad behavior because we have a lot of these very long-running jobs. And if you say scale down, and Amazon happens to choose a machine that's 60 minutes through a 90-minute task, that's actually pretty terrible for us. So we built our own system for this. The first thing we do is look at these active machines, the ones actively doing jobs, and we make sure to exclude those from scale down. But we didn't actually want to choose from just the other machines that were currently running and not doing anything useful to scale down. We wanted to be a little bit more careful than that. So when you think about how Amazon does billing, they round up to the next hour. So if you run a machine for 10 minutes, you pay for an hour. And if you run a machine for an hour and 10 minutes, you pay for 2 hours. So we thought, well, why should we turn a machine off if we've already paid for another 50 minutes of runtime? What if a new job comes in? If we had had that machine running, it could just process it. Otherwise, we're going to have to pay to turn yet another machine on. So the rule of thumb we've come up with is never turn a machine off unless it's within the last 15 minutes of its billing hour. And we found that the APIs make it really easy to go and find out when is the billing hour actually up. So it's just these 4 machines that are viable for scale down. Let's talk about the challenge of having a lack of spot capacity. So normal operations, everything's going along hunky-dory. Spot's scaling up, it's scaling down. We say, let's turn on 2 more spot instances. And it turns out that we can't get them. We get a signal from the API that says there's just not enough capacity and these machines aren't going to be turned on. So our solution to this problem is to run 2 parallel groups with identical launch configs, except for that spot difference. One that only uses spot and one that only uses OnDemand. Now we can open up that OnDemand capacity when we find that there isn't sufficient spot capacity. So in the case of having to use OnDemand instances, we do have to spend a little bit more money, obviously, but it means that we can have service continuity even in the case of insufficient spot capacity. So in this case, we end up using a fair amount of OnDemand, but then as soon as spot capacity returns, we go straight back into using spot. There's a lot more that we can do with Spot at Panopto. We're kind of just scratching the surface. The first one I mentioned earlier was Spot Fleet. So Spot Fleet is a completely different approach to scaling into a cloud of instances. With Autoscaling Groups, you're using one instance type and one machine image. With Spot Fleet, you can ask Amazon to spread your workload across a wide variety of different instances. It's still up to you to determine what instances to use, but you can say, I don't care about running just on a C3 2XL. I'm happy to run on a C3 XL up to a C3 4XL or 8XL. And maybe I'm even happy to run my workload on R3s or R4s. And this allows you to make use of the cheapest machine at any given time. And that can be incredibly useful. You can even define your own custom weighting to determine how much you value a particular machine. You might say that for you, an R3 isn't particularly valuable relative to a C3 because R3s have a lot more memory. You pay much more for the memory on those machines. If you don't have a memory-intensive task, you might just want it for the compute. And so you can say, I want to have the same bid price for R3s as I have for C3s. And I want them to be evaluated as having the same number of compute units. So it can be really, really flexible, and you can tune it very specifically to your environment. There are a few challenges with it, though, that we found when we've started looking into it. One of them is that there is no way to account for the cost of EBS volumes. So when you're running at Spot and you're paying a steeply discounted price for compute, you're still paying full price for EBS. So if you say that you need the same size EBS volume, whether you're running on something like a C3.large as if you're running on a C3.8XL, but you have to run 4 times or 8 times as many C3.larges to make up the full amount of compute that you need, you end up needing to have 8 times as many EBS volumes. And that's going to be a significant portion of the cost. EBS volumes can be 10, 20, 30, 40% of the total cost of your spend. So you do need to take that into account. And there's a couple other problems, like ASGs have very simple health checks. If a machine becomes unhealthy, it can be automatically replaced. It automatically propagates tags to all your machines. These are problems that we think we can work around by using Lambda, but there are still problems. One other big challenge with using Spot Fleet is that if you're using machines of different sizes and different capacity, you need to figure out how your workload applies best to those machines. So in our case, we've taken a lot of care to tune the number of workers and the types of workers that run on each machine. And we've set things up so that they run optimally. So it might be that we can run 3 jobs that encode a video for distribution to phones and tablets simultaneously on a C3.2XL. But if we're going to run on a machine that's half the size or a quarter the size, we might only want to run one of those jobs. Or if we're going to run on a machine that's 2 times as big or 4 times as big, we might want to run many more of the jobs, or we might want to distribute the types of jobs differently. So today we use immutable config. It's baked into the machine image turns on, and there's 3 or 4 workers sitting there ready to go. In the future, we need to be dynamic about that. So the machine comes up, it figures out what type of machine it is and how much capacity it has, and it runs a rubric and figures out what it should do. Another thing that we want to do in the future is move more towards grid-based computing. So if you imagine what's involved in running optical character recognition on an hour-long video, you're going to be pulling all of the video frames out, treating those as images, and running OCR on those images. And that's going to be, as we talked about earlier, a very long-running job. And it's super painful if you lose that machine in the middle. If you subdivide that job out and run it instead of on one machine, you're running it on 4 machines or 16 machines or 32 machines, each one of which is looking at a small portion of the video, then losing any one of those machines is far less painful. You have a lot less work that you have to catch back up. And there's other benefits too, like you can have the turnaround time for that full job be much, much faster because you're running it all in parallel. So in summary, Spot has had a huge impact for our business. We've actually been able to save 53% of our compute on the types of jobs that are running on all the videos that get uploaded. And for us, that's meant that we can take this awesome feature of searching inside videos, and we've been able to give it to our entire customer base, which has been huge for the business and huge for our customers. The other thing is we've been able to save so much money using Spot to run all of the very compute-intensive tasks that we have, that we've been able to turn that back into growth of our business. Most importantly, in expanding our team, which means we're hiring. We'd love to have more strong developers, data scientists, any kind of smart people join us in Seattle, London, and Pittsburgh. Thank you very much.